Hello there, my name is Neil Jersintatilis of BSE1, and today we will be talking about three topics of integral applications. So first off, we have length of a curve. Next is surface area. And lastly, we are going to be talking about centroid of an area. So first off, we have length of the curve. Let's say this is our xy Cartesian plane. Say this is our line or curve denoted by y equals to f of x. This is going to be our b, and this is our a. Now, curve continues on from there, like so. So this is our length of the curve. Now to solve for this, we must first put a strip here. This is going to be our strip. Let me change out the color. Let's have blue. This is our strip here. And then we add dimensions. This here is our y, and to this side it is our x. This strip is, you can say that this strip is our dl, or differential length. And then let's add another dimension from here to here. This side is going to be our dy, and this side here, is our dx. So if we bring this out, better understand, we have here a right triangle, or wait, you can see here, this is our right triangle. This strip here is our dl, this side is dy, and this side is our dx, right? So as you can see, this is a right triangle. We will be using Pythagorean's theorem. So it is hypotenuse equals to sine plus cosine. So dl squared equals to dx squared plus dy squared. Now to solve this, to get the formula from this, we will divide this by dy squared. It's dx, sorry. Let's start with dx first before dy. So next is, we will then have this here. Now as you can see, dx over dx squared is just 1. it can divide to 1. And what we have, and dy over dx is just y prime, right? So what we'll have here is dl squared all over dx squared equals to 1 plus y prime squared. Now to get the square from this side, we will put a square root. So what we have left is dl. This both of this will cancel out, so we have dl over dx equals to square root of 1 plus y prime squared. Now we transpose dx. We multiply dx in this side and this side. Cancel out this dx here to have dl equals to square root of 1 plus y prime squared dx. For the length, we get the integral of both sides. We are left with integral of square root of 1 plus y prime squared dx with limits from a to b. As you can see, this is our formula for this, for the length of the curve here. This is our length of the curve. So this is for our dx, right? So to get our, this time let's get our dy. So instead of dx, so instead of dividing dx here, we will get the dy. So same thing, there's a Pythagorean theorem, dl squared equals to dx squared plus dy squared. You divide it by dy squared. Now same thing will happen just like this, but instead of dx we will have dy. So our answer here is going to be L equals to the integral of square root of 1 plus y x prime squared dx. X prime is from the dy over dx here, and our limits is going to be, let's see, since this dy strip, since this is going to be a dy strip, we have here our c and our d here. There. So our limit is from c to d, like that. Now this is for our dx strip, a dy strip, dy strip, and this is our dx strip. So first let's have an example. We have here number 1, find the length of the curve y equals the square root of x from x equals to 0 to x equals to 5. So we have the graph here for y equals the square root of x, and this is our area, or this is our curve until 5 here. So first let's make a strip here. This is going to be our strip, just like before. This is our y, and this is our x, and make a right triangle here. This is our dl, our dy, and our dx, right? So for this, let's bring out the right triangle here, the strip. We have our dy, dx, and our dl, of course. So if you remember, we are going to be using the dx strip here. If you remember the formula, it is L equals to the integral of a from a to b, square root of 1 plus y prime squared dx. Now, first let's solve for the y prime. Our y is equals to 4, y equals to f of x, right? And our f of x here is going to be our square root of x. So, to get the y prime, we get the derivative of y equals the square root of x. So, y prime is equals to 1 over 2 square root of x. And our limits are 0 to 5, right? So plug in the limits and our y prime, 0 to 5, square root of 1 plus 1 over 2 square root of x squared, and dx here. Next is that we will be using the calculator for this to make it faster. So if you plug in the integral with limits from 0 to 5, square root of 1 plus 1 over 2 square root of x squared, you will get the answer of L equals to 5.64 units, because this is just the length of the curve. So this is our final answer for this. Another example we have here, number 2. What is the length of the curve y equals to 3 sine x from x equals to 0 to x equals to 3 pi over 2? So we have here the graph for the curve y equals to 3 sine x, and this here is our 3 pi over 2. So the curve is going to be just until here. So to get the curve, we will once again use a strip here. There, that is our strip, and this is our y, our x, our dl, and if we put another dimension here, this is going to be our dx and our dy. So if we bring that up, we have here our dl strip, dy dx. Now, using the formula we derived before, we have limits of 3 pi over 2 from 0 with square root of 1 plus, we are going to be using the dx strip again. So our so we will be using y prime squared dx, and our limits of a to b here. So plug in our y prime, our y here is 3 sine x. So to get the derivative of 3 sine x, that is 3 cosine x. So plug in 3 cosine x. There. Now to solve this, use your calculator again. And if you put this in your calculator, our answer is going to be 10.48 units. Okay, that is our final answer for this curve. And that is all for the length of the curve. Next is our surface area. For our surface area, let's put here another graph. Wait, let's put here another graph. There, and just like before, we have a curve y equals to f of x, and this is our limit from b, from a to b. There. Now, this is similar to, let me change the curve. There. Now this is similar to the length of the curve because we put here the strip first, just like in the length of the curve, because the surface area is, see, there. This is our DL strip. This is also denoted as DL, our length. Now this point, from this point here we have Y, and then from this point to here to this point is going to be our X. Now, to understand this, what we're looking for is the surface area. So from this curve here, this is going to be rotated about the x-axis. Remember, from the volume, this is our axis of rotation. Now, if you rotate this, we will have this figure. We'll be having this figure here. So what we are looking for is just this area outside of the volume, and for this surface area, the volume inside is just hollow. The inside of this, let's call this a shell, is hollow, or there's nothing inside, just a thin strip of walls around. Now, let's make here our strip from the DL strip here. There. This is still our DL strip, or our DX strip, I mean. This is our DX strip here. And from here, slide 4, this is our DY. So, if you remember, this here is our Y from the curve to the x-axis. And so for this, we bring out the strip that is going to be just like this one here. Now this is our DL here, and from the axis of rotation, this is our Y. So if we cut this off and then just put here the strip straight, let me make this better. There, this is going to be our strip here. From here is our DL, and the length, this is equivalent to a circumference, so our formula for this is 2 pi r, or 2 pi y. And in the center is our surface area, or the differential surface area. So to get the formula for this, our differential surface area is using a formula for a rectangle. You multiply length and width, that is 2 pi y dl. Now if you remember the dl here, from the length of the curve, our dl is just like this. Here, this is our dl. Let me just put how I put it here. Our dl is either this is our dx. dl is equals to square root of 1 plus y prime squared dx, and for our dy, dl equals to 1 plus x prime squared dy. There, that is our dl here. Now we plug it, we substitute dl. That is going to be 2 pi y square root of 1 plus y prime squared dx. Okay, now if we find the integral of both sides, we will have surface area is equals to the integral of from limits with limits from a to b, 2 pi y square root of 1 plus y prime squared dx. Now this is for our dy strip, right? So if we're going to be solving for the, this is our dx strip. So if we are going to be solving for the dy strip, let's put here another graph. Let's make it black. So another graph. There. Now let's see. Let's have let's say this is our y equals x equals to f of y. And from this, let's say this is our D, this is our C. This is our limits from C to D, and then our strip here, is here. This is our DL, and then we draw the surface area graph for the surface area. Since dy strip, this is obviously going to be the axis of rotation is going to be at the y-axis, so rotate it for about the y-axis, so like this. Now this is our strip, so this is our dx, and then this here, now this is our dy, I mean this here is our dx. Now from this point to the x-axis is still our y, and then from this point here, from this point here, this point is our x. Okay, so just for this, if we bring this out, we are going to have, say, this one, and then another strip there. Our DL is this strip right here, and then our DX is the length from, our DX is the length here. Our dy is this, the length, the width of the strip here, and then this side is going to be our dx. So if we cut this off from the middle, we will make our rectangular strip like this here. Let me make that again. We'll make a rectangular strip from this here. There. Now, just like before, since we are solving for the length of the circle around, the length of the line around the circle, that is the circumference of a circle. So our formula for circumference is 2 pi r, in this case 2 pi y, just like before. But in this case, since it's a dy, this is a dy strip, it's going to be 2 pi x dy. And then center of the strip here is our differential surface area. Okay, just like before, as you can see here, we just substitute y. Let me make a new one. It's our differential surface area, and then 2 pi x dl. We just substitute y, and then for dl we use the dy strip here, the formula for the dy strip, this one here. So dsa is equals to 2 pi x square root of 1 plus x prime squared dy. And if we find the integral of both sides, we have surface area is equals to the integral of from c, with limits from c to d, 2 pi x square root of 1 plus x prime squared dx. There, a dy, I mean. That is our formula for if we are going to be using the dy strip. So we have here the first question, first problem. Find the surface area of a line x plus y equals 4 from x equals to 0 to x equals to 4. About rotated about the x-axis. So this is rotated about the x-axis, right? This is our axis of rotation. So you can see here, this is our graph, this is our line. It's y equals to 4 and x equals to 4 here. So for this, we will first make a strip. This is our DL. Let's make dimension to this side, to the y-axis, that is our x, and to the x-axis, that is our y. Now we will make we'll graph the shell for the surface area. There we go. This is our shell here. Just like before, this is the width of the shell is our dx. Then let us make this here is the shell, the opening of the shell, up to here, since it's on the x-axis. So what we made here is a cone. This is a cone here, as you can see. So if we bring this out, we'll have here the strip. Okay, the strip here, the strip line here is our DL, and then from the axis of rotation to the top of the strip, that is our Y, and this here is our differential surface area. So cut this off, just like before. We will make a rectangular strip, just like this, and then this is our DL and the 2 pi y, and this shaded area is our DS, differential surface area. There. Now to solve for this, once again, just like before, this is differential. This differential surface area is equals to, just like the formula for rectangle, the area of a rectangle, multiply the width and the length, that is 2 pi y dl, and dl is equals to square root of 1 plus y prime dx. So let's substitute that is 1 plus y prime squared dx. Now find the integral as a, and integral with limits from a to b, and our limits here is 0 to 4. 2 pi y, 1 plus substitute y prime. Our y here is our given line. Our line here is x plus 4, right? X plus y is equals to 4. We transpose x here, then our y is going to be 4 minus x. So our dy, or the differential of y, is going to be y prime equals to negative dx or negative 1 dx. So let's put here negative 1 squared dx. Now solve for this. Let us put it in our calculator again. This whole equation here. And what we'll get for our surface area is 71.08 square units. It is square units because we're looking for the area of the surface of the cone. This is our final answer. Okay, second problem here. We have number 2, find the surface area if the curve y equals to 1 over x from x equals to 1 to x equals to 4 is rotated about the y-axis. Now, this is similar to example I've given up earlier. So in this case, we are going to be using our dy strip. So first, make a strip here. This is our dl, and then make a hollow curve. Let me move this. There. Now we'll make a hollow shell. There. This is our strip. And then from here is the opening of our, or from here is going to be the opening of our there we go. Just like that. Now let's remove that. This is all we need for now. And then what we're looking for is the x strip. We'll look for our x. What's given is the curve y equals to 1 over x. Now if we multiply x and then divide by y, we'll have x equals to 1 over y. Right? So, and then our limit here is this is 1 here, and what we're looking for is this. So to find that, we will plug in for this x here, and that will result to 1 over 4. So our limits is from 1 over 4. Our limit is from 1 over 4 to 1. So then this is a dy strip. Axis of rotation is on the y-axis. As you can see here, it is rotated about the y-axis. So bring this out. We'll have a hollow strip here. Now the strip here is our dl, and the width of the strip is our dy. It's now our dy. And the axis of rotation, from the axis of rotation to the edge of the strip is our x. Right? So if we cut this off just like earlier, it will result in a rectangular strip of 2 pi x dl, and shaded area is our differential surface area. So using the formula, you can derive it like this. So substitute dl. Since we are using the dy strip, we are going to be using the square root of 1 plus x prime squared dy. Now find the integral of both sides. We'll have surface area equals the integral with limits from c to d. Our c to d here is from 1/4 to 1, right? 2 pi x. Substitute x. Our x is 1 over y square root of 1 plus our x prime is, let's see, our x is 1 over y, right? So to get the derivative of x, we'll have x prime is equals to negative 1 over y squared, right? So substitute x prime here, negative 1 over y squared dy. Now if you plug in this equation on the calculator, you would have an answer of 48.49 square units. That is our final answer for this. Next up, we have centroid of an area. Now for the centroid of an area, just like before, we'll make another graph here, and then our curve there. This is our limits from A to B, and then our strip is going to be this here. Now we shade the strip, and the centroid we are looking for is on the middle of the strip right here. This is our centroid, the dotted line, and the dot here. Now what we're looking for is the xc and the yc. That is the position of our centroid, or that is this c. Let's denote centroid as c, right? And this x, y. This is what we are looking for, the position of the c. So erase this. You can see here, from the strip to the x-axis, we have our y, and then the width of the strip is our dy, dx, and from the strip to the y-axis is our x. Now, since the position of the centroid is here on the center of the strip, we'll have our yc here, That is equals to, since this is half of a y, that is y over 2. And then the distance from centroid to the x-axis is still x, right? So what we're looking for is our, just like before, the centroid xc and yc, that is equals to x bar and y bar. Okay, so if we're looking for the yc, first let's bring out the strip here. This is our strip, and then the width of the strip is our dx, as you can see, and then from here, from the top to the bottom of the strip is our y, and since the center is at the center, it is y over 2, right? And that is what we're looking for. So see yc here is equals to area 1 area sub 1 minus yc minus yc here. Wait, this is, let's say this is x bar a1 minus yc over the total area, or a dot, that is equals to, area 1 is going to be make it blue. All the area here is our total area, and that is y, right? So let's put in y here. The limits from a to b is y. This is times, I forgot. I'm sorry. This is times a times yc. So a, that is integral from with limits from a to b y dx multiplied by integral with limits from a to b y over 2. This is our yc, right? Dx all over our 8, since we only have one here, that our total area is still the same as this. There. Now simplify, we'll have one half y squared dx over y dx, and that is our formula for our y bar. And for our x bar, we have a sub 1 multiplied by x c, or our centroid for x, and the total area once again. So that is equals to our a sub 1, that is still integral with limits from a to b y, and our xc is simply just x, so that is xy dx all over our total area, still the same. There, that is our formula for our x bar, and this is our formula for our y bar. There. And what we're looking for the centroid is our c equals to yc xc and yc, or that is x bar y bar. Okay, so number one, we have find the centroid of a quarter circle. As you can see, the circle is x squared plus y squared equals to 4. If you can understand this, x squared plus y squared from the formula, this is uh, 0 and 0. So it starts from the origin. And since our radius is 4, from the original formula it is x squared plus y squared equals to r squared. And our radius, if we square root this, that is equals to 2, right? So you can see this is you can see the distance from the origin is 2 and 2, since it's a circle. Now, and since we are only looking for the quarter circle, this is what we have, a quarter of a circle. Now, first off, this is our area here, and then since we're looking for the centroid, we put a strip here, and this is our centroid here. So just like before, this is yc equals to y over 2, because from the top of the strip to the x-axis is our y, and then distance of the strip to the y-axis is our x, and the width of the strip is dx. As you can still remember, and this is our x sub c. Now, first let's bring out the strip. We have here a strip there, and this is our centroid. The distance from the top to the bottom of the strip, that is our y, and distance from the center to the bottom of the strip, or you can also use the top, but let's use the bottom, that is y over 2, or yc equals to y over 2. There. Now this is our dx, our width, and the center is our dA, or differential area. So we have here yc is equals to y bar, right? Is equals to a times yc over the total area, or a dot. So this is equals to integral from, as you can see, our limits is from 0 to 2 here, so let's plug in the limits, and then y over 2, our area is y and our yc is y over 2, so if we join them, we will have 1/2 y cubed dx all over the total area, which is simply y dx. Now to look for the y bar, we plug in our y, that is our y from, let's get the y from that is transpose x, we'll have y squared equals to 4 minus x squared, and then get the square root of both sides. We'll have y is equals to square root of 4 minus x squared. So if you plug it in here, we'll have equals to 2, bring out the constant 1/2. That is let's say this 2 here. That is equals to 2. 4 minus x squared, that is squared dx all over. Let's put just y here, there. But for the total area, we are going to use, since it's a circle, we are going to use pi y squared over 4, pi r squared over 4. That is the area that we are going to use, since it's total area pi r squared over 4, since that is the formula for the area of a circle. And our r here is 4, right? Our r is 2, and since it's squared, it's going to be 4. So 4 pi over 4 cancel out both 4. A is equals to pi, so we'll have pi dx. Now if you plug it in on your calculator, you'll have the answer of 0.85 square unit, 85 units. I mean, since we are looking for the location of the centroid, this is our answer for y bar. Next is x bar. Since this is a dy strip, this is going to be easier. Say a sub 1 times xc over a dot, or the total area of a circle. This equals to integral from with limits from 0 to 2. The xc is just x, and then our total area is y dx, right? All over a total, just like before, it is just pi 0 to 2 dx. Now, if you plug it in, we'll have the same answer of 0.85 units. There we go. Solve it on your calculator. This will be the result. That is our final answer. So our centroid is at 0.85 and 0.85. That is our final answer. Okay, next problem here is the centroid of the area under the curve y equals to 2 sine x from x equals to 0 to x equals to pi. Now, as you can see here, this is the curve of y equals to 2 sine x with limits from 0 to pi here. This is our area. Show the area is what we're, and then our strip is, let's put a strip here, there. Now this is our center at the center of the strip. So just like before, from the top of the strip to the x-axis is our y, and then distance from the strip to the y-axis is our x, and the width of the strip is our dx. Now for the centered, distance of the center to the x-axis is y over 2, since it is at the center of the strip, and then the distance from the center to the y-axis is our xc. And this is our yc, that is equals to y over 2. There. Now, first let's bring out this strip here. We have strip, and then our dx, our y, and the center is here, so we get that out. That is our yc equals to y over 2, with shaded area as our dA, or differential area. That is equals to y dx, using the formula for the area of a rectangle. So if we find the integral of both sides, we'll have a equals to the integral of y dx. Okay, so this is what we need to find the total area. So first, let's find the y bar, that is equals to a yc over a total area, or a tot. That's 8 multiplied by yc. This equals to, just like before, our a is the integral y dx, and our yc is y over 2. So if you multiply y and y over 2, that is y squared over 2. And our limits is from 0 to pi, as you can see from the graph here. And don't forget the dx all over the a total, that is y dx. Now let's plug in the y. That is, let's bring out 1/2. Our y is y equals to 2 sine x, so 2 sine x squared dx all over integral with limits from 0 to pi. We have 2 sine x dx. Now if you plug in the whole equation in the calculator, you'll have y bar is equals to pi over 4. Now this time for the x bar, we have this equals to a multiplied by xc over a total. So this is equals to limits from 0 to pi. We have x as our xc, since it's just the length of the strip to the y-axis is just x, and then our a is y dx from here all over a tot, or a total, still the same as that, squared with limits from 0 to pi y dx. Now plug in y. We have x 2 sine x dx all over 2 sine x dx. There. Now plug this in on the calculator. You'll have x bar is equals to pi over 2. Now this is our answer here. Let's see, centroid, there. The location of the centroid is at point pi over 2 and pi over 4. There. That is our final answer. That is all for this video. I hope you enjoy. I hope you learn from this video. And that is all.